Waiting for water to boil must be the slowest moment in the human history, right?
You've probably heard the saying, a watched pot never boils.
Feels like the more you stare at it, the slower it heats up.
But is this just a trick of the mind, or could there be something scientific going on?
This question is at the heart of the boiling pot paradox, a seemingly simple yet mind-bending mystery that connects everyday life to some of the most perplexing ideas in science. Hello, my name is Lilith, and today let's solve a riddle and try to understand the science behind the boiling pot paradox. So the saying "watched pot never boils" brought me to an old riddle, the Riddle of Three Sisters. It seems simple on the surface, but has a twist.
Three sisters are given a curious task by their father. Each is presented with a pot on the stove covered with lids.
Similar pots, similar stoves. Scientifically speaking, everything is under identical conditions.
The father declares, the one whose pot boils first will marry. The first sister is eager, her heart set on marrying. The second sister doesn't care, indifferent to the whole affair. The third sister, however, has no intention of marrying at all. She would rather avoid it. The question is, which sister will marry?
Write your ideas in the comments, and while you're thinking, let's try to understand why the pot never boils when you try to make something like spaghetti.
This is mostly about psychology. When you're waiting for something and focusing intensely on it, time seems to slow down. For example, eagerly waiting for a phone call, a text, or a pot of water to boil. Seconds stretch out, feeling like minutes.
Scientists have a name for this phenomenon: time dilation. But it's not the kind that happens when you're close to a black hole or on a spaceship that is flying close to the speed of light. Instead, it's a brain trick. Our perception of time gets distorted when we're fixated on an event.
Your brain becomes hyper-aware of the passage of time when you're focusing on something, which makes it feel like time is moving slower than it is. This is why you could stand in front of a pot, stare at it, and feel like it's taking an eternity.
In reality, the water is heating up at the same rate as if you weren't watching it. It's just the more you concentrate on the process, the longer it feels. But that's just one piece of the puzzle. What if there is more to it? What if there is something happening when you stare at the pot for so long? Maybe act of watching influences the process. Now here's where things get even more intriguing. In quantum mechanics, there is a concept called the observer effect, which suggests that simply observing a system can alter its behavior. At first, this might sound like something out of science fiction, but it's one of the cornerstones of modern physics.
Simply put, in quantum mechanics, measuring specific properties of tiny particles, like electrons or photons, changes their state. The famous double-slit experiment is a perfect example. When photons are fired at a screen with two slits, they behave like waves, creating an interference pattern. But when we measure which slit a photon passes through, the interference pattern disappears, and the photons behave like solid particles instead. The mere act of observation changes their behavior.
This phenomenon is known as wave-particle duality, the idea that particles can act as both waves and particles depending on how we observe them. In this case, observation collapses their wave-like nature into a definite particle state. The system no longer behaves as it would if left unobserved. But let's get back to our boiling pot for a moment. At the first glance, the quantum physics has nothing to do with a simple kitchen experiment. After all, water isn't a quantum system. It's not made up of single electrons or photons. Yet the idea that observation can influence a system is something that extends far beyond the quantum world.
Could our act of watching a pot of water actually affect its boiling process in some way? While the observer effect is typically reserved for subatomic particles, this connection forces us to ask, how much do we really know about how observation impacts the physical world around us?
as in the riddle about the sisters. At first it seems like an easy answer. If conditions are identical, then water will boil at the same time in all pots. But as minutes pass, the situation becomes more mysterious.
The first sister, eager to marry, repeatedly opens her pot, checking to see if the water is boiling. The second sister, indifferent, leaves her pot untouched. The third sister, who doesn't want to marry, opens her pot in hope of finding the water still unboiled.
And every time when the first or third sister opens the pot, they lose the precious heat from under the lid.
So the one who's least involved, who remains the most detached, finds her pot boiling first. She's the one who ends up married.
The riddle shows how seemingly small actions or inactions can change the course of events. The act of observing or not observing shapes the outcome in the way that seems impossible to predict. In this case, the person least interested in the outcome gets what she never wanted. A strange twist of fate, perhaps. Or is there something deeper?
Greek philosopher Zeno argued that if you observe an arrow in flight at any single moment, it appears to be motionless. It occupies a specific position in space and isn't moving. Since time is made up of series of instants, and at each instant the arrow is at rest, Zeno concluded that motion must be an illusion.
Of course, we now understand motion through continuous change rather than discrete snapshots. So the paradox doesn't hold in modern physics. However, it has an intriguing quantum counterpart, known as the quantum Zeno effect.
This is the idea that frequent observation of a quantum system can freeze its state, preventing it from evolving. It's based on a principle that measurement affects quantum particles. Imagine a particle that's supposed to decay over time. If you continuously measure it, the decay process holds, and the particle remains in its original state, as if each snapshot of observation prevents it from moving forward.
But could this principle apply to something as ordinary as boiling pot of water? The short answer is no, at least not in the way quantum mechanics describes it. The quantum Zeno effect only works on microscopic quantum systems, while boiling water is far too large to be influenced by this phenomenon. But it raises an intriguing question. Could observation, in some subtle or unexpected way, affect the physical world around us? Like a strange, real-life version of a watched pot never boils. While this is purely speculative and doesn't have any practical application to boiling water in your kitchen, it helps to illustrate how observation and passage of time are intimately connected, especially at the microscopic level. The idea that we can freeze or slow down a process simply by watching it opens up fascinating possibilities for the future of science, technology, and maybe even our everyday lives. As we move from the abstract world of quantum mechanics to the more grounded science of boiling, things start to get a little clearer, but no less fascinating. When you heat water, it eventually reaches 100 degrees Celsius at the sea level and starts to boil.
How much is it in Fahrenheit?
But once it hits this temperature, the water doesn't get any hotter even if you continue to add more heat. Why does the temperature stop rising even though you're supplying energy to the pot?
The answer lies in the latent heat of vaporization, which is the energy required to change a substance from one state to another without changing its temperature. In this case, from liquid water to steam. When the water reaches its boiling point, all the additional heat you provide breaks the bonds between the water molecules, turning them into gas. This concept isn't exclusive to water. The same principle applies to other phase changes, like the melting of metals or the boiling of liquids. The fascinating thing about these transitions is how they seem to challenge our everyday understanding of how heat works.
But let's consider this further. What would happen if you could somehow bypass this phase transition? What if you could keep increasing the temperature of water beyond its boiling point? The consequences of that would lead us into the realm of extreme physics, where our current understanding of matter begins to break down. So let's take this idea of boiling to the extreme. exploring what might happen in a hypothetical situation. Imagine you have a perfectly insulated pot, no heat escapes.
You place the pot on an infinite heat source, continuously adding energy to the system. In theory, the temperature of the water should keep rising, approaching infinity.
If energy were continuously added to the system, the temperature would rise, eventually reaching what's known as Planck temperature, about 1.4 times 10 to the 32 Kelvin. This is considered the highest possible temperature beyond which our current understanding of physics breaks down.
The behavior of matter itself becomes chaotic. The pot, the water, and even the very concept of temperature itself would no longer follow the rules we understand today. While this idea is more about pushing the boundaries of what's possible than something we could ever actually experience, it's a reminder of the limits imposed by nature.
You see, the universe has hard limits, and our understanding of the cosmos is built on these fundamental principles. Even in something as seemingly simple as boiling water, these limits shape how we perceive the world around us.
The idea of a pot absorbing infinite heat without any losses is purely fantastical. Yet it serves to highlight just how intricate and complex even simple processes like boiling can be when viewed through the lens of science.
The boiling pot paradox isn't just a quirky thought experiment. It's a window into the way science works. How seemingly simple processes can be tied to deep, complex principles. When we look closely at something as ordinary as boiling water, we're reminded that the world around us is full of fascinating mysteries. Whether it's the psychology of time perception, the strange phenomenon of quantum mechanics, or the well-understood physics of boiling, the act of waiting for the pot to boil reveals much more than we first realized.
It shows us how deeply interconnected everything is in the universe, from the subatomic particles that make up matter to the larger processes we can observe with our naked eye. This interconnectedness reveals a key truth about the nature of reality. And sometimes it's not just about answering questions, it's about asking more. As soon as we think we've understood one part of the puzzle, new questions arise that push us further into the unknown.
And the more we explore, the more we realize how little we know. The boiling pot paradox in its simplicity serves as a microcosm of its larger journey of discovery. It invites us to constantly question the world around us, challenge our assumptions, and look for answers even in the most mundane of places. So next time you stand in front of the stove waiting for water to boil, take a moment to appreciate the science behind it. Think about the energy flowing into the water, the molecules breaking apart to form steam, and the strange interplay between observation and reality. And if it takes forever, just remember, it's not the pot, it's your brain playing tricks on you. Or is it? Maybe, just maybe, the universe is hiding its secrets in plain sight, right there on your stove. Thank you for your time. See you in the next video.